So I don't know if any one of you has really done this exercise. If you have a cat at home, you hold it upside down, about this height, and you let go. You've done it. I've seen it happen. We don't have a cat, but I have a friend who has a cat, and she did it for me. It was very pleasant. We were sitting in the sun, like the beautiful sun you have here in Santa Barbara. And the most remarkable, well, you know, the cat did a little maneuver and landed on its feet, because cats are supposed to land on their feet. But the most remarkable thing to me at the time was how bored the cat looked. He was really not impressed by this exercise. I was, and I'm going to talk about it for an hour. Okay, so I also don't know. So this is supposed to be a picture of Baron von Munchhausen. I'll tell more about Baron von Munchhausen. How many people in the audience grew up as children with the stories of Baron von Munchhausen? Can I see? How many have no idea who is Mr. Baron von Munchhausen? Okay, so I'll tell you more about Baron von Munchhausen, but it's a collection of in some places known as children's stories. It's actually not children's stories, about the Baron, and he was a good, tall storyteller. And many of the stories there are outrageous. And one of the stories, outrageous stories, the person was a real person. He actually fought in the Russian army against the Turks. And most of the stories have something to do with the war. And in one of the stories, he had to run away from the front on his horse. It was at night, and they both got bogged in a swamp. This horse couldn't get out, and they were slowly sinking. The Baron was, however, a very strong man. So he pulled on his hair and dragged both of them out. So this is one of the stories of the Baron von Munchhausen. You didn't giggle, but you're supposed to giggle. And the basic theme of this talk is going to be, why do you giggle when you hear, oh, you didn't giggle. Why do you giggle when you hear the story about the Baron von Munchhausen bootstrapping himself, and you don't giggle when I tell you the story about the cat? You see, the problem is like this. The cat starts with 0 total angular momentum. This is how I started it, upside down. It landed on its feet. By Newton's third law, a cat cannot, nor anybody else, cannot apply a self-torque on itself, and therefore the total angular momentum of the cat should remain 0. It started at 0, it would remain 0 no matter what maneuver the cat does. So this means, but it landed on its feet. It means that a cat can rotate with 0 total angular momentum. Okay, now let's turn to the Baron. The Baron, suppose the Baron is here. He's not in a swamp. Let's make it a little simpler. He's just in free space. His total momentum is 0. Again, by Newton's third law, he cannot apply a total force, net force on himself. So his total momentum should remain 0. Why can he not repeat the trick of the cat and displace himself with 0 total momentum? What's the difference? So I'll talk about it for an hour. So here are the questions I posed. A cat rotates without angular momentum. Why can't the Baron displace without momentum? This talk I will give various other examples of this talk, but this will be an illustration where motion is related to things that we know more in quantum mechanics, which is called Berry space. And I will explain to you that had Baron von Munchhausen lived not in a curved space, he would be able to bootstrap himself, and we will discuss this. somehow the running theme about this talk would be the fact that things don't commute. So motion would be generated by commutation. I'll explain all these notions. I think an alternative title to this talk would be what I've learned from Oded Kennett, who really was the driving force about all this motion in curved space. But I talked with Amos Ori, who is a general relativist in our department. The basic idea that motivated this work was Jack Wisdom. Jack Wisdom was the first person to realize that Baron von Munchhausen could bootstrap himself if he lived in a curved space. In fact, let me tell you this. Jack Wisdom was interested in the following question. He's a planetary scientist at MIT, and he was interested in the question, suppose you are near the horizon of a black hole, and the engine of your spacecraft died. Could you swim away from the black hole? Could you do some crazy maneuver, use the fact that near the horizon the world is curved, and just escape by swimming? So he wrote a nice science article that I was influenced by, and this is basically reflections on what he said. So just to let you know, in principle, the answer is in principle yes, in practice no. So in principle yes means that you can bootstrap yourself, but you'd have to make tremendous maneuvers, and you'll move Planck length or something like this. You'll move very little. Many of the ideas are geometric, and this owes to things I learned from Frank Wilczek. And on the bottom line are people I worked with, like Oren Raz, who was my student, Omri Gat, Boris Gutkin, and David Arknin. I'll mention some of these things later. I think I told you about Friedrich Hieronymus Freiherr von Munchhausen. That's when he lived. He was apparently a nice, decent gentleman and a good storyteller. Many of the stories which were assembled in the books of Baron von Munchhausen predated him. You know, they were just embellishment on the truth. Okay, so let's start with business. So let's start with a very primitive model of a cat. So as I mentioned before, the cat manages to rotate with zero angular momentum. I want to show you how you can do this. Now, what the cat can do, well, a rigid body cannot do that because angular momentum is related to the angular velocity. So if you rotate, you also have angular momentum. But if you are not a rigid body, you can rotate without angular momentum, and I want to explain how. So the cat, being a deformable body, can do things like stretching. So here on the left, on the top, you have what do I mean by stretch. Let's take a cat which is a square. You know, physicists usually start with a spherical cat. I will start with a square cat. So you start with a square cat. The cat can, you can imagine that the cat is made of a piston, right? So the cat opens this piston, and I call this operation stretch. If you look at it, it is clear that there is no angular momentum is generated by this. Is it clear, or should I draw a picture on the board? That think of 4-point masses. If you think of 4-point masses like this, and you put here a piston and here a piston, you open both pistons, you see with your eyes that you satisfy Newton's third law, and there is no rotation which is generated, but what is generated is a stretch. Now, a stretch, if you represent it, what is the generator of a stretch is a matrix which has 1 and -1, 1 in the x direction because you open, -1 in the y direction because I contract. I wanted to preserve the volume of the cat. This is, I don't allow him to conflate. The other thing the cat can do is it can shear, which basically means it stretches in the 45 in this along this direction and contracts along this direction. And this is represented by a matrix which is sigma x. Now, notice both matrices are symmetric. This is a reflection of the fact that there is no rotation, and they represent deformation. Now, the nice thing is that the commutator of x and y, x and z, is an antisymmetric matrix, which you recognize as the generator of rotation. So if the cat has two controls, which is two stretches, which are independent, and he makes a motion which is a commutator, he can rotate. Okay? So the commutate, right? So here is a little mathematical animation that just does this. So I make a sequence of two stretches. You see the object rotated by about 45 degrees. So this is how you generate motion by commutation. So you see it's kind of nice. You may be more used to that on the plane. In fact, a good plane, what you have in a plane, you have a rudder that allows you to rotate this way. You have, I forgot what's the name of this thing, ailerons, which allow you to do this way. And you have, I forgot the name about these things. Flaps? No, not flaps. Right, the thing, in the stick, in principle, in the stick, you can push up and down. This allows the plane to go up or down, or right and left. Then you bank this way. And there is also a rudder which you control with your legs, which rotate this. In fact, the commutator of any two gives the third. So in principle, you could make a cheaper plane by... So this is a similar idea, except that, right, with the two control, you create something that you had no control over. So you make a rotation from deformations. This idea that you can you control things in life by commutation when you don't a priori have control will play a key role in this talk. Yeah? Someone was? Okay. Now, and second element that when we'll go into this talk is that it's sometimes nice to think about elementary problems in mechanics as a problem in gauge theory. So we don't tell students when we teach them in first year, elementary mechanics, that rigid body motion is an example of abelian gauge theory. But let me explain it. In fact, there is aspects of it which are non-abelian, but let's consider this very simple case. So rotation of a rigid body is a well-defined notion. I don't have to make any convention a priori. But what is translation of a rigid body depends on a choice of a fiducial point. It's not a well-defined a priori concept. For example, if you consider this wheel moving on the plane, then if you take your fiducial point, the contact point, then its velocity is 0. If you take your fiducial point for translation, the center of the wheel, it's the velocity of the bicycle. And if you take the top point, it's moving twice the velocity of the bicycle. This is so the notion of translation depends upon a choice of a fiducial point, which I can think of it as a choice of a gauge. Since translations basically commute, this is you don't see the richness of gauge theory in this story. This is a practically useful observation, because it means that when you ride a bike, you can't avoid getting dirty on your back by paddling faster, because the top thing is always moving at twice the velocity that you are moving. What can you do? Now, once we move from non-deformable bodies to deformable bodies, we get into non-abelian gauge theory, and let me explain that. Because if you are a deformable body, like, say, this inchworm thing, then even the notion of rotation depends on the choice of a frame. you saw that the notion of translation depends on the choice of a frame of a fiducial point in a rigid body. In a deformable body, you also have to decide, is this guy, depending where you stick your frame, you can decide if this guy rotated or did not rotate. So translation and rotation now become contingent on a choice of a frame. So here is an example, again, an animation. Let's hope it works. So here is a deformable body. If you decide to choose the frame anchored to this arrow, then the body is not rotating. But if you decide to choose your frame anchored to this body, it is rotating. Now, in either case, and this is going to be important, there is a gauge invariant notion that emerges when the body makes a periodic change in its shape. Right? So after the body completed a cycle of change of shape, you can determine uniquely by how much it was translated and how much it was rotated. So this is an analog. This is an analog of something we recognize in gauge theory, that the vector potential is gauge dependent on an open loop. This thing is ill-defined, but if you consider a closed loop, it gives you a gauge independent quantity. So this is just a... Okay, so now let's get back to the Baron. So why did we giggle when we hear the story of Baron von Munchhausen? This is because Newton says that the Baron cannot do that. Now, this is one thing that happens when you, in modern life, you can appear to be more erudite than you really are by just asking Google, how did Newton formulate his law? And here it is in Latin, corpus omne perseverare in statuo sivo quiescendi del movendi. I won't continue. I don't know it, Latin, of course, but anyway, this is anyway. The words are sufficiently simple that you can figure out what he's saying. So the modern translation would be: a body preserves in being at rest or moving uniformly, except insofar as it is compelled to change its state by force impressed. Actually, I don't know. At least at the Technion, we don't teach it this way. We say something a little simpler. The center of mass of a system will remain at rest in the absence of external forces. This means that the center of mass of the Baron plus the horse cannot, if it started at rest in empty space, it will remain there forever. Okay. That's true, right? Newton was careful, right? But I really want to talk about this notion of center of mass. This is going to be a central notion in my talk. It is true that Newton didn't use it. Well, so I told you that the Baron can displace himself if he lives in curved space. And the question is, what goes wrong in this theories, in these laws of Newton? Oh, the laws as I wrote them here. Anybody is willing to guess? So what goes wrong? Did Newton make a mistake? Do we teach students something which is wrong? Where is the catch? So while you are thinking, I'll tell you a joke. So the people are complaining about the level of education, I guess, all over the world, but especially in Israel. So the story I want to tell you about this college professor who is teaching his students about Newton's third law, which says that the force that the horse applies on the cart on the right is the same and opposite to the force that the cart applies on the horse. This is Newton's third law. And the student says, but teacher, why is the cart nevertheless moving in the direction of the horse? and not vice versa. To which the teacher says, I guess the horse is pulling a little harder. Okay, so why you so anybody is willing to take what's wrong with Newton's law as I formulated them here? There is an implicit assumption that Newton made, and we all make, and we don't mention it when we write these laws, but like all laws, they depends on something. Nobody? You're so... Who said this? You're close, but no. Now, Euclidean space. Newton assumed that space is Euclidean. And as I shall explain to you, the center of mass motion is an intrinsic Euclidean notion. If you move away from Euclidean space, the notion of center of mass becomes problematic. So let's do this. So the simplest example I can think of having a space which is non-Euclidean is I live in one dimension, but the world is a circle. So like, living on a screen of a computer. I disappear on this end, and I come on the other end. And so let's ask the question. So we live on a circle, which is a one-dimensional space. And I ask you, what's the center of mass of these 2 point masses? So there are 2 ways to proceed. One way to measure the distance on the upper arc and say that the center of mass is sitting up there. The other way is to say that the center of mass sits down here. And the third way to say that you don't know what is an abstract one-dimensional circle. It has to live in 2 dimensions, and then the center of mass doesn't even live in the space. It lives somewhere else. Now, so you see that if space is not Euclidean, in this case it's not Euclidean by topology, the notion of center of mass is ambiguous because there are 3 candidates. Now let me show you that once center of mass is ambiguous, you can transport yourself. So here is how you transport yourself. You need to be schizophrenic to do this. Right? So you can start as a ball with a spring. The spring opens, you move, and you recombine on the other side, recharge the spring, and you're happy on the other side. So this is an illustration of the fact that center of mass is a Euclidean notion, and once you have ambiguous center of mass, you can displace yourself. This example is a little boring, I think. Here is another one. I want to show, even without crazy topology, it's just to have enough to have interesting geometry for center of mass to be problematic. So let's consider 3 point masses, identical point masses, in Euclidean space. And I want to find out what's the center of mass of these 3 masses. Now, there are various ways of doing it. And the nice thing in Euclidean space is that no matter how you do it, you get the same answer. So let me explain what do I mean by this. I can first compute the center of mass of these 2 point masses, which is here. It's midway between the 2 by the geodesic that connects them. And then the center of mass between mass 2 and mass 1 on the other vertex, I put in a ratio 2 to 1. And this is the green point. Now, you could do it in a different order. Start not with this pair, but instead start with that pair. And it's a miracle of Euclidean geometry that medians in a triangle intersect, and they always intersect at the 2/3, the same point, which is 2 to 3. If, however, you lived on a sphere, you could still do the same exercise. You would connect 2 masses by geodesic, and you could decide that the center of mass of a pair is midway in between the 2. But now the result would depend on the order. Why? Because the median don't intersect at 2/3. They intersect elsewhere. So the center of mass becomes ambiguous. And now I'll show you this idea of Jack Wisdom, that if center of mass is ambiguous, you can transport yourself. So now we have a baron, which is these 3 masses. The baron has a piston connecting these 2 masses and another piston connecting this pair, and he can control the 2 pistons. I think it is clear to you that, for example, by opening the first piston, the center of the baron is not displaced. They move up, they move down, but there is no motion along the equator. And if you open this piston, then again you don't move because this piston moves to the right, this mass moves to the right, these two move to the left, and what you would think of as a center of mass stays at the same point. However, let's watch the movie. So the guy is doing commutation, right? It's doing commutation. And it's displacing itself. Now, I think, when you see animations, you don't learn anything, right? Perhaps I cheated. Perhaps I just wrote a computer program that moved the sucker, huh? So I want to convince you the only way to convince you is by explaining it on the board. But I think if I write it on the right, the guys on the left won't see it. Okay. If I do it on the left, the guys on the right won't see it. So let me explain how this works. So here is the sphere. Here is the equator. And we start with these two balls like this. And to explain the ideas, oh, wonderful. But, oh, that's enough, I think. Then it becomes usable. So let's start by opening this piston. To illustrate ideas, I open it all the way till this mass is at the North Pole, and they are moving along geodesics, and this mass is at the South Pole. This piston is massless. It's a Gedanken piston. Okay, so I send things to the North and South Pole, and now I have this thing. Now I open this piston, and I pose a question to the audience. Who is going to move? So there are two possibilities. One is that I open the piston, and this mass would move to the right. Another possibility is that I move the piston, this mass would stay put, but this very long piston from the North to the South Pole would move to the left. And a third possibility is that will be some mixture. Now, quiz. Who votes for the first? Who votes for the second? Who votes for the third? So basically, I should have given a four conclusion. Who doesn't care? Now, this cannot move. Why? Because you can think of it as angular momentum, conservation of angular momentum. If this were to move, there must be some torque because there would be angular momentum generated about the z-axis. However, if I just move the piston, it's a fictitious thing. It costs nothing. These guys just stay at the North Pole, and the piston moves like this to the left. Okay? So now I open this piston, and now I can bring these guys back, and I can close the piston. I can close the piston. Now they would move at a ratio 2:1, and then at the end of the commutation, we moved a little bit. Okay, so this example was actually pointed out by Jack Wisdom in his science article. Now here is something which is really amusing, which I'm going to illustrate in the next thing. So if you are Euclidean, which is the limit of this thing when R is infinity, you can't move, right? This is what Newton told us. If we live on a sphere which has positive curvature, and you do this exercise, swimming like this, you move up. But since things depend now on the curvature, I would ask you the question, you continue making the same maneuver, but I now move you from a space of positive curvature to a space of negative curvature. How would you move then? Anybody is willing to guess? You're a very quiet audience. So this is now a motion on a negatively curved surface, right? Because the one radius of curvature is like this, the other one is like that. And the funny thing is like this. You continue to make the same maneuver, but now you move backwards. Okay? So it would be nice to see, say, a swimming competition in this world. You know, you see these guys crawling like this, but they're moving backwards. It's like... Okay. Good. Good. So now let me set some theoretical framework to discuss this issue of swimming. So I want to think of swimming like a control problem, that there is control space here, which is denoted by this plane, and this is shape space. So what a swimmer can do, it can control its shape. I can do this. And the swimmer is constrained to make periodic motion in its shape. So it's making strokes. In this plane, it looks like a stroke. But I want to plot the behavior where in the additional axis I describe Euclidean motion. So after the swimmer has completed the change of shape, it may or may not be displacing itself, right? So it's an issue of holonomy. There is a closed cycle in control space, but an open cycle in full space, which is both the shape and where the shape is located. So this is a nice framework to think about this. And now, let me say something about shape space. So shape space is a big place. The simplest, almost simplest shape I can think of is a triangle. And a triangle is determined by its three lengths. They also have to satisfy triangle inequality. So it's described by three real numbers. And therefore, the shape is described by a point in 3 space, in fact, by some cone in 3 space. And therefore, a periodic stroke would be some periodic closed curve in R3, or in this cone. Okay, so that's fine for a triangle. Now let's move to a more complicated object, say C60. Now what do I mean by a shape of a C60? Well, one possibility to say what the shape is to say that I fix all mutual distances. I say that this is the shape by fixing all mutual distances. So then the shape is a point in some big space. How big a space? 60 choose 2. This is a huge number of dimensions. But now think about it like this. So shape space is huge space, but in any fixed geometry, if I give you some Euclidean space or some curved space, I give you some space, how many degrees of freedom do you have? You have 60 atoms. For each of them, you have 3 coordinates. So the space you live in only gives you 180 degrees of freedom. What does this mean? This means that most shapes cannot be realized in the world you live in, right? So some shapes would live in Euclidean space, 180 dimensional thing will live in some space. Now you deform the space to some other space, and there will be 180 other dimensions. So shape space is a big thing. Now, why am I telling you all this? I'm telling you this because I explained at the beginning that you can't swim in Euclidean space because Newton is against you. Now, it turns out you also can't swim in a generic curved space because geometry is against you. In a generic curved space, which means that the curvature here is different from there. At every point it's different. You'll be lucky if you can find a place where you meet. At most places, you just don't fit. Now, let me illustrate this by something. You know, this is what archaeologists do all the time, right? They have a rigid body, and they get fractions. And a fraction would fit in one place. It doesn't, if it fits here, it doesn't fit anywhere else. This means that if you had a swimmer that did periodic motion after a period in a generic curved space, it must be back at the same point it started. So Euclidean is no good because of Newton, and generic curved is no good because you are lucky if you fit anywhere if you are rigid. You actually know this from life. You don't need need to tell you this, right? Okay. So in a generic space, the position of shapes are locked. So in order to formulate a reasonable swimming problem, we have to consider spaces that are homogeneous and isotropic. I saw you brightening up. In fact, symmetric spaces with constant curvature everywhere. So the typical examples are like this. So it's a property of Euclidean space. You are a rigid body. If you fit here, you also fit here. If you fit here, you also fit rotated. But this happens also in other spaces. For example, if you leave the surface of a sphere is homogeneous and isotropic, and there is this upper half plane, a caricature of which I try to draw here. It actually cannot be embedded in R3, but it has constant negative curvature. So I'll consider motion on symmetric spaces. Why? Because if I want to consider periodic change in shape, this is what I'm forced to do. Okay. I have a quarter of an hour. Okay, so killing fields. It's getting worse, right? No? So killing fields are, well, here is my definition. A killing field is a vector field on the manifold you live in, and it induces motion that does not create any strain in the body. So it's basically, so in Euclidean space, the examples of killing fields are translations, which is this vector field. If you take a rigid body and you translate it, you don't deform it. Or rotation, which is this killing field described here. It's this vector field, minus yx. Note that this killing field is a constant in Euclidean space, but this is not, right? It's the vector field associated with rotation. Now, these killing fields are defined in general if you have a symmetric space. So on a symmetric space, they are homogeneous and isotropic, and therefore they admit such fields. Okay, now I want to show you, this is the only serious pseudo formula that I'm going to show to you. No, not everybody is asleep yet. So here it's an amusing thing is, as I try to explain, you can swim in curved space because momentum is zero. Okay? So let me explain how this works. So we have particles with mass mn. N is the index of the particle. Each particle has momentum mn xn dot. And I want to consider the conserved momentum, which is the component of the momentum of the particle in the direction of this killing field. So think in the Euclidean case that I look at the momentum in the x direction, or if you want, at the angular momentum. So this defines this object on the left, which is conserved. If originally the cat or the Baron was at rest, all the particles were at rest, x dot was 0, and I started at 0. And therefore, I have 0 equal to this object. What's written here? The psi is taken from here. I took this x dot, and I multiplied by dt. So now look at this equation. What does it say? It says that if we change the motion of all little masses that make the body, there is a constraint, right? Which is fixed by the conservation law. Now I want you to think of this dx in this following form. I divide it into two pieces. One, which I'll call the rigid body motion of the whole body, and the other pieces, the transverse pieces, which I'll call the control. This is what the object can control. Okay, so if you write this dx schematically in this form, and you substitute in this equation, you can rearrange the equations written here. There will be as many equations as killing fields, and I will get a linear system of equations which will determine the rigid body motion in terms of the deformation with the help of some matrix. This is a vector in some huge space. This will be a vector in 6 space, 3 for rotation and 3 for translations. And this will be some rectangular matrix. Okay, so this is the problem you need to solve. you have a differential equation which determines how much you move when you, in the control space, you take a path. And it's a fact, a well-known fact about differential equations, that when you move the control in a cycle, you, in general, acquire some holonomy. Now, in general, this is a difficult problem, but you can make some progress if you consider very small cycles like this, and then you can avoid solving differential equations. Now, I won't bother you with this detail, but I think one thing which is clear from this expression is that you will be able to swim only when psi is a non-trivial function of xn. It turns out that this is indeed the case. And a motion in a direction associated with a killing field psi is possible only if space is such that curl of psi is different from 0. So now I will give you a reinterpretation of why cats spin and barons lie in Euclidean space by looking at a killing field. So why cat can spin? Because the killing field of rotation is minus yx. If you look at its curl, this is 2. It's different from 0. However, for translation, the killing field is a constant. Its curl is 0, and therefore the baron cannot shift itself. However, if I live in a general curved space, the killing field satisfies a certain differential equation where you don't have to really pay attention to what differential equation it is. The only important thing is that psi is not a constant if r is not a constant. And if you work it out, you can find out this formula which was derived by Odette Kennett and says the following, that if you are a body living in some symmetric space and you perform a stroke whose size in control space is dA, then you move by an amount which is A times R. R is the curvature of space. And here is a property of the body. It is made from its x coordinate and y coordinate. This is a motion in 2 dimensions. So it's some complicated formula. I just want to point out one little thing. You see, if you are a small body, this scales like your size to power cubed. The other natural scale in the problem is r. Okay? So if you are small compared to the size of the world you live in, you move very little. This is why in this example made by, if you are near a black hole and you want to swim away, you can't. At least it's very ineffective. So this is the only formula I wanted to explain. And now, to end this talk, I want to tell you about other cases of motions by commutations. Okay, so parking is an example of motion by commutation. It's, again, similar to this. So if you have a car, you have the gas pedal, which allows you to translate in the x direction. You have a steering wheel, which allows you to rotate. You don't have wheels that allow you to do motion in the y direction. You don't have this control. I had an uncle who wanted to invent such a car with 4 wheels, you know. I'm sorry, it's 8 wheels, 2 on this side and 2 on that side, so that you can park in tight spots. But this was misguided, right? Because the commutator of dir and drive is park. This is how you park, right? You commute. And so what do you know from this? Well, commutations are difficult to figure out. This is why it's difficult to park. But the more important moral of this is like this. If there is a tight parking spot, then the steer and drive are small, of order epsilon. And the commutator is of order epsilon squared, which means that the amount of maneuvers increases quadratically when the size of the... You know this too, right? Okay. This is something everybody can relate to. So here is another example of... how am I doing with time? No, I have 5 minutes. I'll skip this example. This is the one which is, of all the examples, this is the one which is relevant to reality, so I'll skip it. Let me explain another last notion of motion, which is geometric, which is a little bit related to this. You know, there is I didn't mention so far topology, and I wanted to mention topology in this talk. So let's now do swimming in a Fermi sea. You can do that too. I mean, previously the Baron was swimming in empty space. I think it's clear, right? Now we want to do some swimming in a quantum fluid. Okay, so here is our swimmer. The swimmer is an object which sits in a one-dimensional Fermi sea. It's a finite swimmer, and think of the swimmer that it's basically scattering electrons, right, in the Fermi sea. So think of the swimmer that it is a scattering matrix. For example, you can think of a triatomic molecule where some daemon allows you control the distances between the pairs of atoms. Okay, so when you control the distances, the scattering matrix associated with this object will change. So now you can do the same thing in the space of scattering matrices. You can make a cycle. Now, normally, when we learn scattering theory, we do scattering theory like this. We take a scattering object and we pin it to the origin. And then we ask, what does it do to particle scattering from it? But now I want to play a different game. I take a scattering object. I make it do a cycle in scattering space, but it's not anchored. It will accommodate its position to make Newton happy. And what does Newton say? Newton says that if the swimmer is controlling its shape adiabatically, he's not allowed to transfer momentum to the bath. Okay, so there is instead of a condition that the swimmer stays at the origin, it's a condition that no momentum is imparted to the fluid. Okay, now it turns out, I don't think I can describe the theory that goes into this. It's analogous to the theory of quantum pumping, except that pumps usually are anchored, and when they do some exercise, they move electrons from right to left. Here, the pump is not anchored, and instead of pumping things from right to left, the pump has to move. So here is an amusing result. So a quantum swimmer, after a stroke, moves by a quantized distance, always. What's the distance? It's always an integer multiple of half a Fermi wavelength. Now, shall I explain this, or you're already overwhelmed? So I won't explain it, but I'll give you an exercise to think why it is half and not 1. Okay, I think I want to finish on time. But there is if you want, there is by the way, geometric interpretation of this integer, which I'll give you. And I could also explain a little bit, but let me not. So you see, here is control space. Suppose it's 2-dimensional. And we are considering, as I said, it's a t equals 0, so that the Fermi energy is a well-defined concept, and in 1 dimension. Now, it's a fact, I don't know if you know this fact, that if you have 2 control parameters on a scattering matrix, you can always make the scatterer transparent by choosing a point. What does it mean that the scatterer is transparent? For example, you want the scattering matrix to be 1. It's a complex number, but it has to be 1. So you need 2 conditions. But you have 2 parameters. So with 2 parameters, you can satisfy 2 conditions. Okay? So this means that if you take a path in control space, in general, the path would enclose points that if the scatterer would be here, it would be transparent. And in some sense, the integer here just counts how many points of transparency there are. Okay, so now let me finish. So what did I try to tell you? That I tried to give you collections of examples where you swim by commutations. It's always a little bit has a geometric flavor, which if you like geometry is nice. I find it intriguing because very often when you do commutation, very often it's difficult to decide a priori which way you would move, right? So I don't know if it happened to you when you parked and instead of moving towards the, you moved away, but it's just an issue of order. If you do things in the wrong order, you move in the opposite side. So it's intriguing, and it is very ineffective when the strokes are small, but it can be effective when you are allowed to make big strokes. Right, so I don't know. I could tell why I picked these two pictures, but I think this is now 3 o'clock. It's a good time to stop. Thank you.
So we have time for questions.
Hans.
Why did you pick up those pictures?
So you know, after we figured out this theory of swimming in curved space, we already knew that you can't rescue yourself from black holes. So I wanted to think of a different application. So here is a putative application, right? So you know, it's all a little bit on shaky feet, but nevertheless, let me illustrate the idea. So the world we live in is not flat. It's not Euclidean. It has some curvature. It's true that it's curved in space-time and not space. So let's forget about this. This is the weak feet. So let's just think that we have some galaxy which is living on, and space is curved, right? Now inside the galaxy there are stars, so it performs some periodic motion. As a consequence, it would displace itself, right? So here would be an example of a motion in curved space. But again, for the same reason I explained before, the motion would be minuscule, right? Because unless the galaxy was so large to be essentially the finite fraction of the universe, it would move by very little. So this was this picture. And this picture was, there are these little animals which are called water striders, and they walk on water. Their motion is actually complicated hydrodynamics because they shed vortices. But suppose it lived on suppose you lived, or some animal lived on, you were very small, you lived on a bead of water, you know, and you wouldn't create these things, but you wanted to move on this bead of water. You could move with this theory, right? So
can you make an engine using general relativity where an object curves the space around it and then uses that curvature to move?
I've not thought about this.
I bet you can prove it's impossible.
But what you want the object to control the space is?
Right.
Well, this is beyond what I was talking about here. Here I was just talking about motion in a fixed background. Right. You don't control the background. You just use the given background. You know, you use the curvature as a kind of a anchoring points to climb a rock. Hans, yes, you were.
Well, first I should thank you because now finally I have an answer, to all the leave comments when you try to parallel park. I can tell them that, it's an E-square effect. But also, when you do parallel parking, I guess everybody knows that the first move is very important. You do the first move wrong, then you can go on forever. So is there any way of incorporating the importance of the first movement
what I described here, this commutation between rotation, this is a very rough description of parking. You could take a much more serious description of parking. And in fact, my colleague and friend, Jean-Pierre Ekman from the University of Geneva, told me he once made, you can make this, I never did, this is just beyond me, but you can make a very nice exercise of how would it be to park a 6-trailer car. It's apparently a well-known problem in control theory, and it's known to be a very subtle one because it depends on many derivatives. So these drivers know how to make, but I can't say anything else.
So this motion, swimming, say I swim in a parabolic, right? Then because it's like a adiabatic process, so I move by some fixed amount after a periodic motion.
Yes. It doesn't have to be adiabatic in the case I discussed, but
what is set the limit? Because I can't move very, very fast than the speed exceed the speed of light.
you know, this is the theory I described was classical Newtonian mechanics. It was not relativistic.
So what happens when I move very, very fast? And try
You
to
mean when you want to generalize this to do a relativistic theory?
Yeah.
You know, I didn't do this on purpose because Jack Wisdom worried about rapid motions in relativistic motion. I did not want to do it because I thought that this classical mechanic problem would be a nice problem to think about. So I've not thought about the problem you're phrasing. I think all these notions when, you know, if you know that special relativity leaves a great discomfort with the notion of rigid bodies, right? And in particular, you would have to discuss what you mean by the shape coming back to itself. What does it mean that it makes? So I didn't want to worry about this question, so I really did not treat any relativistic thing.